Welcome to Chapter 9 of Class 9 Science, Gravitation. In this fascinating chapter, we'll explore the invisible force that keeps our feet on the ground, makes apples fall from trees, and holds the entire universe together. We'll journey from Newton's famous apple to the motion of planets, understanding how gravity works both on Earth and throughout the cosmos. Get ready to discover why what goes up must come down, and much more. Let's begin with the story of how Isaac Newton developed his theory of gravitation. The famous story tells us that Newton was sitting under an apple tree when an apple fell on his head. This made him wonder, if Earth can attract an apple, can it also attract the moon? Is it the same force? And why doesn't the moon fall to Earth like the apple does? Newton realized that the same gravitational force governs both falling apples and orbiting moons. The moon is constantly falling toward Earth, but its forward motion keeps it in orbit. This is similar to when you whirl a stone tied to a string. The string provides the centripetal force that keeps the stone moving in a circle. If you release the string, the stone flies off in a straight line. Similarly, without gravity, the moon would fly off into space. Now let's explore Newton's universal law of gravitation in detail. This law states that every object in the universe attracts every other object with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. The mathematical formula is F equals g times m divided by d squared, where F is the gravitational force, g is the universal gravitational constant, m and m are the masses of the two objects, and d is the distance between their centers. This law applies to all objects in the universe, from apples to planets. The gravitational constant g has a very small value, 6.673 times 10 to the power of -11 Newton meter squared per kilogram squared. This explains why we don't feel gravitational attraction between everyday objects. The force is too small to notice. One of the most important distinctions in physics is between mass and weight. Mass is the amount of matter in an object and is constant everywhere in the universe. It's measured in kilograms. Weight, on the other hand, is the force with which a planet attracts an object. It equals mass times acceleration due to gravity and is measured in newtons. Your mass is the same on Earth, on the moon, or in outer space, but your weight changes because the value of g changes. On Earth, g is approximately 9.8 meters per second squared, but on the moon it's only about 1.6 meters per second squared. This means if you weigh 60 kilograms on Earth, you would weigh only about 10 kilograms on the moon. Interestingly, the value of g varies slightly even on Earth. It's greater at the poles and less at the equator due to Earth's shape and rotation. When objects fall toward Earth under gravitational force alone, we say they are in free fall. During free fall, objects accelerate downward at a constant rate of 9.8 meters per second squared, if we ignore air resistance. Galileo famously demonstrated that all objects fall at the same rate regardless of their mass. He supposedly dropped different objects from the Leaning Tower of Pisa and found they all reached the ground at the same time. This seems counterintuitive. We might expect heavier objects to fall faster. But the reason is that although heavier objects experience greater gravitational force, they also have greater inertia and require more force to accelerate. These two effects cancel out exactly, so all objects accelerate at the same rate in vacuum. In air, light objects with large surface area like feathers fall slower due to air resistance, but in vacuum they fall at the same rate as heavy objects. We can use equations of motion to solve problems involving objects moving under gravity. For free fall, we use the same equations as for constant acceleration, with A equal to g. For example, if an object is dropped from rest, its velocity after time t is versus equals g times t, and the distance fallen is s equals 1/2 g times t squared. If an object is thrown upward, it slows down, stops at the maximum height, then falls back down. The time to reach the maximum height equals the time to fall back to the starting point, and the speed when it returns equals the initial speed. These principles allow us to calculate how high objects go, how long they take to fall, and their velocities at different points. Now let's explore what happens when objects are immersed in fluids. When an object is placed in a fluid, it experiences an upward force called buoyant force. According to Archimedes' Principle, discovered in the 3rd century BC, the buoyant force equals the weight of the fluid displaced by the object. Whether an object floats or sinks depends on the relationship between its weight and the buoyant force. If the weight is greater than the buoyant force, the object sinks. If they're equal, the object floats partially submerged. If the weight is less than the buoyant force, the object floats completely submerged. This explains why heavy ships made of steel can float. They're designed to displace a large volume of water, creating enough buoyant force to support their weight. Buoyancy has many practical applications in daily life. Ships float because they're hollow and displace a large volume of water. Submarines control their buoyancy by filling or emptying ballast tanks with water. Hot air balloons rise because hot air is less dense than cool air. Hydrometers measure liquid density by how high they float. Even swimming is easier in saltwater than freshwater because saltwater is denser and provides more buoyant force. The relative density or specific gravity of a substance, its density compared to water, determines whether it will float or sink. If relative density is less than 1, the object floats. If greater than 1, it sinks. Gravitation isn't just an earthly phenomenon, it operates throughout the universe. The value of g varies on different planets and moons depending on their mass and radius. On the Moon, g is about 1/6 of Earth's, which is why astronauts could jump higher and carry heavy equipment easily. On Jupiter, g is about 2.5 times Earth's. You would feel much heavier there. Earth's specific gravity is crucial for life as we know it. It's strong enough to hold our atmosphere but weak enough to allow rocket launches. It creates the right pressure for liquid water to exist and drives tectonic activity. The Moon's gravity causes ocean tides, demonstrating that gravitational effects extend across vast distances. As we conclude this chapter, let's review the key concepts. Newton's universal law of gravitation explains how all objects attract each other. Mass is constant while weight changes with location. All objects in free fall accelerate at the same rate in vacuum. Archimedes' Principle explains buoyancy and why objects float or sink. These principles have countless applications, from space exploration to navigation to engineering. Gravitation truly is the force that rules the universe, governing everything from falling apples to orbiting planets. Remember these concepts as you observe the world around you, and you'll see physics in action everywhere.